had derived this equation involving G. Okay, G is a function of h, small h, and which is nothing but cos theta. And from there, we said, okay, I can assume, or I can write it down, the G of h as a series in h. Okay, so series expansion in h. So it will be given by a0 plus a1h plus a2h square. So you have infinite number of terms. A general term would be a nu times h to the power of nu. And then what you can do, you can take a derivative of this. G prime means first derivative of G with respect to h. Also, you can take the second derivative, and then you can just calculate all the quantities here. Okay, this time second derivative, and then what you do, you just add them together so that you get this differential equation, which is equal to 0. Now this is true for all values of h, whatever the value of h, and this is possible only when all the coefficients for all the values of h are 0. So in general, we take the coefficient of h to the power of nu. So you just collect the coefficient of h to the power of nu. So I have shown you the coefficients. These are the coefficients with this minus sign. And if you take them and then put them together, so you see that this is what you get. This is all the coefficients. If you add them, is equal to 0, and this gives you a prescription to calculate this coefficient a nu plus 2, or rather express a nu plus 2 in terms of a nu plus a nu. I think I should be somewhere here. Yes. So this is a nu. So a nu plus 2 can be expressed in terms of a nu. This is called recursion relation. And you see that this is given by this expression, that a nu plus 2 is this. I think yes, I have one thing missing here. I should have one a nu here. Which is there, this a nu. The whole thing is multiplied with a nu. Okay. So I know a nu plus 2 in terms of a nu, and then I'll say, okay, see, I cannot deal with an infinite series because my wave function has to be well behaved. It has to be square integrable. So the series I should truncate or should terminate. I cannot go beyond a power in h. So let us assume that, okay, any power in h which is nu plus 2 onwards is 0. So for that I just put a nu plus 2 0, this coefficient for h to the power of nu plus 2 0. And if I put a nu plus 2 0, which basically means the numerator shown here is mod m plus nu plus mod m plus nu plus 1 into mod m plus nu plus 1 minus beta has to be 0, which basically means beta has to be equal to this, and I define a new quantity nu plus mod m as small l. So beta is written as l into l plus 1, and this seems quite familiar to some of you. And let me recall that m is the magnetic quantum number. I'll also again show you, and m can have values like 0, plus minus 1, plus minus 2, like this. And the nu is just a coefficient for the series expansion, and we had assumed that nu varies from 0, 1 to 3. Okay, it is not 1 to 3, it should be 0 here. 0, 1 to 3. 0 is also possible. Okay. So once we do this, so what we have here, that L, which I have defined nu plus mod m, the lowest value of nu is 0, lowest value of m is 0, so the lowest value of L is 0. So basically the lowest value of L is 0, and it also tells you that your L has to be greater than or equal to mod m, because nu varies from 0, 1, 2, 3, like this. So the next value would be 1, next value would be, then the next value would be 2, like this. So L has to be greater than or equal to mod m. When m is 0, L is 0, then L is equal to mod m. But for any other value of m, so plus minus 1 or plus minus 2, anything, L is greater than mod m. Okay, and then we went back to the theta part. Okay, we had beta, we replaced beta with L into L plus 1, And once we express the element L plus 1, we did some algebra. There is some fine problem. I have fixed it. Okay. And you will see that this is how the equation looks like. Okay. And this equation would have one term, which is L into L plus 1 divided by R square of this constant. And I told you that this, if you do the classical mechanics of the problem, this problem belongs to what is known as central force problem, where your interaction potential depends only on R, no theta phi dependence. And for such problem, the angular momentum is conserved. So angular momentum is angular momentum is R cross P. L is R cross P. I have written it somewhere here. Yes, R cross P. So this is conserved. So what happens, for example, if I consider an electron at a distance r from the nucleus, and if the electron can come even closer to the nucleus. When it comes close to the nucleus, your r value decreases. But in order to keep your angular momentum L constant, your momentum, linear momentum, should increase. Your r cross p is your L. If r decreases, p should increase so that their cross product remains constant. So in other words, angular momentum is a constant of motion in this case. So if the electron is close to the nucleus, then the energy associated with the angular motion of the electron is will be higher. It will increase rather. It will increase as you bring electron close to the nucleus. So essentially, if I go back, so this term is account for the energy associated with the angular motion of the electron, because we had already got rid of theta part. Okay, and because of that, it has come here. This part, this thing has come here. This is the energy associated with the angular motion of the electron. And also you can say this is something like centrifugal force in classical mechanics. Anyway, so this is the structure of the equation. I have this is the radial part of the equation, which is dealing with the kinetic energy due to radial motion, and then you have this and this. So you can see this has now become a part of the potential. It's like a potential. This is Coulomb potential, and then you have an extra potential because you have already solved the angular part of the problem. And then we made some substitution. We said, okay, I define a quantity rho, which is twice alpha r, and we did some algebra, and I'm not going to go through this. And eventually, you can write down a differential equation in terms of capital S. Okay, so just go back. Capital S is your r when you express r in terms of rho. So that's a function. Capital is a function. And this, if you look into this equation, you will see that 1 over rho square, 1 over rho, this kind of terms are there. So in the limit, when rho is very, very large, in the asymptotic limit, and rho, you remember rho is proportional to r. Rho is twice alpha times r. R is the radial distance. Right? When the electron is far away from the nucleus, these terms will vanish because it has 1 over rho square, 1 over rho kind of behavior. So I can have something like asymptotic solution to this differential equation, and I can have a solution like a constant time exponential rho by 2, or a constant time exponential of minus rho by 2, okay, like this. But I cannot take plus rho by 2 because if I take rho by 2, then this function has a problem because this is not going to be square integrable, or it will not vanish when rho goes to infinity. So I have to take exponential of minus rho by 2. So the general solution would be exponential of minus rho by 2 times a constant. No, it is true only when the asymptotic limit. For any value of rho, it has to be something like exponential of minus rho by 2 times another function of rho. This is how you did. Then we did some algebra. If you are interested, you just can go through, and we put back this f as f times exponential of minus rho by 2 here. Did the algebra, and then we did the same series expansion. That's slightly different here. You have rho to the power of s. S is not the capital S, small s, something like this, and then you a0 plus a1 rho plus a2 rho square the bracket, and you do this, and then again you collate all the coefficient of first you can collate the coefficient of, for example, rho to the power s, and when you collate the coefficient of rho to the power s, you will see that you get two solutions for small s, either small is equal to L or small is equal to minus L minus 1. But I said you cannot take small s equal to minus l minus 1, because if you take this, your rho to the power of s will become rho to the power of minus l minus 1. And then when you are close to the nucleus, yeah, your density, your rho will diverge. So the only solution you can take is s equal to s. Okay. For example, if I take L equal to 0, then it is 1 over rho. So when rho approaches 0, 1 over rho will blow up. So that's why I'm saying that not the rho, I think I should have said the function itself will diverge. Okay. So whatever the function, that will diverge. Okay. So I have to take s equal to L. So the good thing about that now, okay, I have s equal to L, small s equal to L. And then we did the same thing what we did for the theta part. We collate the coefficient of a nu plus actually coefficient of rho to the power nu plus s, and from there actually we can calculate evaluate coefficient of a nu plus 1, actually expressed in terms of a nu. This is the recursion formula. And again, I have to put the numerator 0, and that gives you lambda, which is equal to nu plus s plus 1. I call this lambda small n. This is nothing but principal quantum number, you'll see. And the small n is given by nu plus L plus 1. Okay. So now look at this very simple expression that small n is nu plus L plus 1. You know, the lowest possible value of nu is 0, lowest possible value of L is 0, so the lowest possible value of n is 1, which basically means that n minus 1 has to be greater than equal to L. This is another condition I have found. Okay, now lambda equals to n, we have found, and we had defined lambda earlier. If you go and see your note, you see that lambda was defined like this, because when you did that solve the differential equation, we put some constants together and called that constant lambda. This is lambda. Okay, and also we had a constant alpha square, which was given by minus 2me by h square. Since E is negative, this alpha square is always positive. E is negative because if the electron is far away from the nucleus, energy is 0. As you bring the electron close to the nucleus, the energy decreases and becomes negative. Okay, that is how it is defined. So now what I can do, I can just make use of these relations. What I can say, okay, alpha square is this. So let us, this is alpha, this is lambda, which is n, which is given by this. So alpha square is this. So now from here I can calculate alpha. Alpha is this, and then I take x square of this alpha, which will be alpha square, and that I equate to minus 2me by h square. And if you do this algebra, you will see this is the expression for energy. En is minus mu to the power of 4 divided by n square h plus s square times something. You can see this. Remember, n is 1, 2, 3. The very important thing is that here the energy is not continuous. Energy depends on n. It is 1 over n square dependence, minus 1 over n square. N is 1, 2, 3 like this. So basically means only some energies are allowed, not all the energies. So what I see here, it is nothing but quantization of energy, because we have this quantum number, this is called principal quantum number. So energy is quantized, and this expression actually matches exactly with the expression given by Bohr in his theory, old quantum theory of atom, where you have circular orbit and electron is revolving around nucleus in a circular orbit, and the expression is exactly the same what you get here. Okay, so we'll start from here today. Actually, the recap. So how many of you had seen the video? I don't know, but so please tell me whether you want to ask any questions from here, or maybe we can do it later because it is a bit mathematical. But the whole thing is that you must follow this part, because it gives you actually an idea how these quantum numbers come and how the quantization takes place in quantum mechanics. Remember that it is because of the truncation or termination of that series. We have to terminate that series, because I cannot take infinite series. It will not give me a well-behaved wave function. In order to have a wave function which is well-behaved, I have to terminate the series. Okay, and that gives you quantum numbers. And what is important here, that in case of hydrogen atom, you see that the energy depends only on one quantum number, that is principal quantum number n. Okay, so we'll start from here today, and I hope that you guys go and spend some time on today's talk and day after talk. Okay, so again I'll recall. Okay, you had this Hamiltonian. So can you see the Hamiltonian? Remember this Hamiltonian? We had this, no? Can you see it? Yeah, someone tells me.
Yes, sir.
Yes, sir.
Yeah, yeah, yeah.
Yes, sir.
So don't get scared. I'm not going to ask you a question like write it down. Okay, I don't expect you to remember. Okay, this is Schrodinger equation. A psi equal to E psi essentially. Psi is for the relative coordinate. And this is what we assume. This is a product of function of r, function of theta, and function of phi. Remember, all of you? This one you should remember. The product of three functions. Say yes. With the unmute and tell yes. I
Yes,
hope.
sir.
Yes,
Yes, sir.
Yes,
And
sir.
then
Yes.
we had this. Yeah. Then we had this. I'm just highlighted the phi part. We had the phi part, and this is equal to minus m square. I could have equate this to some constant, any constant c, but the convention is that you put minus m square. And remember, this m is not mass. This is a quantum number. This is actually called magnetic quantum number. Okay. And we had solved this equation also. So we can put back in the main equation. So I had another equation involving theta, and that I said is equal to minus beta. So that I also can put back to the R equation. It will have this. We have solved this equation, kind of solved it actually in the last class. So the thing is that we did not really solve the last equation. We said that if you solve the theta part, you get some functions. I'll tell you what are those functions. And if you solve the R part, you also get functions. The phi part is very simple. You remember exponential of plus minus im phi kind of solution. Theta part has this p of h, and h is cos theta. H means small h, and then you have other things also. So that p of h and yeah. So if there is a name for this, and I think I had said in the recorded video, that is called associated legendary functions. Okay, and when you solve the R part, and you get what is known as Laguri polynomials. Okay, you should know the names at least. Okay, so but the structure is like this. But what I've seen that R part depends on n and l, two quantum numbers. Theta part depends on l and m. Very precisely, it depends on L and the mod of M, and phi part depends only on M. Okay, so this is a radial wave function, and theta and phi string together. This is called angular part of the wave function. And actually, if you put y, theta, and phi together, I don't know whether you know this. If you put theta and phi together, has anybody know what is this called?
Spherical harmonics.
Yes, this is use capital Y L mod n. This is called, these are functions called spherical harmonics. Okay, so that is quite useful. I expect you to remember the names and the structure. Okay, the way I have written, not the mathematical expressions. Okay. This is fine. As I told you.
Yes, sir.
And if you see carefully, quantum numbers L varies from 0 to n minus 1, M varies from 0 plus minus 1 like this, plus minus L is a manic quantum number. And also I had derived the expression for energy, and if you go and look into the expression, it is exactly the same. Okay, I just replace H cross with H. H cross is H by 2 pi. We had H cross S square. If you put that, will be H cross S, H square by 4 pi, 4 pi square kind of thing. Okay, so and that will give me, eventually it will give you this kind of, yeah, tell me.
So you obtained in from the equation that was mu e to the power 4, but
Yeah,
can
yeah.
we replace that with m?
M is, okay, sorry, the notation is different. M is, it should be mu, but M is the mass of electron, which is very close to mu, isn't it? If you are very, because mu is what? Mu is
1 by m plus 1 by small m.
Yeah, mu is okay. This is very large, isn't it? M is very large, so 1 by small m is very close to 0, isn't it? So mu is very, very close to m. That's why I put the mass of electron there. Okay.
Okay.
So m is the nucleus mass of the nucleus, which is much heavier than electron. So exactly this expression, and this expression you can calculate, and you see that it has a structure like minus 1 over m square. Okay, times a constant, and I can make my life easier by writing it like this, and then I define something like A0. A0 has a name. This is called Bohr radius. We'll talk about it later. It is some radius. It's actually the radius of the fast Bohr orbit, if you do the old Bohr theory. And you can write this energy divided by hc. Okay, you know, when you define by energy, this is wave number. In terms of wave number, this is something like Rh by m square, and Rh is given by this. This is called Rydberg constant. And so the lowest possible energy state is n equal to 1, which is E1, which is minus of Rh. Next one will be minus of Rh by 4. But you see that as I increase the quantum numbers, your energy levels come close to each other. No, they're coming close to each other. So eventually, in the very high n limit, they will almost superimpose on each other, and will go to what is known as continuum, and will hit what is known as the classical limit. So as my n increases, your system go more towards classical. It starts behaving classical. And the limit when n is very, very large, n goes to infinity, gives you the classical limit. This is a quantum classical correspondence. Okay. So, but these things I think you have already know from your Bohr theory. But what we have shown here, that even solving the hydrogen atom problem, you can actually come up with the similar expression. Okay, but then why would one do hydrogen atom? And the answer to this is here. So how many of you can see this slide?
Yes, sir, we can see.
Yeah. So first of all, don't get scared, because I am not going to ask you to remember this situation. I am not going to tell you write down the expression for theta. No way. Okay. No way. Okay. So as I told you that I have the wave function is a product of three functions, r, theta, and phi. Phi is very simple, 1 over root over twice phi exponential of im phi. You remember this? This is how it is. We have done this, no? The 5-part solution. Theta part, you remember that we did something that PL cos theta. We had assumed when we had started like this, and then we have something coming here. This is nothing but the normalization constant. So the whole thing is that this wave function, we'll do in the next slide, it has to be normalized. I'll tell you how to normalize it. So theta is given by this expression, and this PL, this is called, this has a name, this is called, can anyone tell me what is this PL cos theta? Can you tell me?
So, like associated Legendre polynomial.
Can you tell me what is this PL cos theta? Maybe you write down in the chat box. What is PL cos theta? Yes, this is called associated legendary polynomial. Okay, I'm not going to write it here, but you remember, okay? And then if you see, I'll come to that later, but R of this is also given by exponential of minus rho by 2. Remember, that is asymptotic limit. Then rho to the power of L, because you remember that you have found we have rho to the power of F times sin something. So rho to the power of L, because eventually got small f equal to L. So you have rho to the power of L, and then you have capital L. I'll tell you what is 12 plus 1 n plus L. Okay, so this capital, not here, the capital L given here, this is a name. This is called Laguri functions or Laguri polynomials. Okay, this is called Laguri polynomial. How many of you know Laguri polynomial? Heard about Laguri polynomial? Okay, only one or two. And you said that you know hydrogen atom. Only one and two. Okay. Now let me again tell you what is there. But again, I tell you, you don't need to remember these things. Okay, what you need to remember? You have to remember this and the phi part, these two. All the other things you don't need to remember. Okay, only the psi and the phi part. Total psi is written like this, phi part. And also you should know that R depends on NL, theta depends on L and M. Strictly speaking, mod of M, and phi depends only on M. Okay. Now this, let me concentrate on the theta part. Theta part tells you that you have some constant times PL cos theta. This is called associated legendary function. And you can, mathematician have knew about all this. They had solved already differential equations of this structure, so they knew the solutions. And this is how it is written, this PL of Z. Z is the argument. Z is like your h, small h, is given by this expression. You have to take a derivative of this quantity. We have a L sitting there. So if it is P0, then L will be 0. So which basically means you don't take any derivative. P1 means you take first derivative. P2 means you take second derivative, like this. Okay. You have power also here sitting there. This is the way to calculate this, your PL from this. Okay, this is PL, but then you have another expression which is PL is this part only, but you have to, if you take the derivative of this PL with respect to this, like mth derivative of PL with respect to Z or the H. I had H here, I have put Z here, so I have H in my expression. Anyway, this is given by this expression. You remember this, I think. I hope you remember. At least you should remember this. Remember that we have written PLH equals to 1 minus Z squared to the power mod M by 2, something like that. It's coming like that. If you go and see your expression, you will see that this is how it is. But you have a formula to calculate this PLMZ from PLZ, like here. Similarly, the R part is quite complicated. This constant gives you the normalization constant, and then you have exponential of minus rho by 2, rho to the power of L, and this L. Now this 12 plus 1, okay, n plus L, what does it mean? In general, this L is given by this expression, exponential of rho, derivative of this quantity, Rx derivative of this quantity, that gives you L. And if you have LRS, it is actually the Fth derivative of LR. So basically this capital L, 12 plus 1 of n plus L, means it is the 12 plus 1 derivative of capital L n plus L. Okay. And you have these quantities rho and A0. I have put Z here. Can anyone tell me what is this Z? Capital Z here, not the small z. Can anyone tell me?
Atomic number.
Yes, because what I have done, we have done it for hydrogen atom. It is also true for any system which has one electron, but you have more number of protons. For example, helium plus. So Z is 2, or lithium 2 plus. But you have 1 electron. So in general, you can choose an atomic number like Z and put it there. Okay, that is a very general expression. So don't get scared by looking at this expression. Okay, you don't need to remember this. For example, I can give you this expression and I can ask you to calculate the wave functions. Okay, that is one possibility. So let us try to do it. Can you do it? Let us try to do it. These are the expressions. Okay, so which one should I do? So I will do the easiest one. Okay, usually the teacher, he does the easiest one, isn't it? So let us do it. Just using the formula, just calculate this. So the easiest one would be your psi 1 0 0. Now you understand why? Because it's the lowest, the ground state of your hydrogen atom, isn't it? This is the ground state of hydrogen atom. Because if I write psi 1 0 0, what does it mean? It basically means the principal quantum number is 1, n equals to 1, l equals to 0, and m equals to 0. Actually, I think you guys would know this. This is nothing but your psi of 1s. Because all the wave function I've written here, this wave function for the hydrogen atom, these are known as the orbitals. So orbitals are nothing but one electron wave function. Okay, we'll talk about it later again. Is this fine if I write psi 100 as psi 1s? You understand this? Huh?
Yes, sir. Yes, sir.
Yeah. This is not very difficult. Now I have to calculate this using this formula. Don't get scared. Math is not scary. So we will calculate phi part of it. What is phi 0 then? Because it's a product of the r, theta and phi. No, the phi part. Let us calculate the phi part. This is phi 0, isn't it? What is the answer? You know?
1 over root 2 pi.
Yeah, it is exponential of 0, which is 0. So I'll have 1 over root over pi, twice pi, isn't it? Very easy. You will see this is true for all, almost, yeah, because essentially it has no phi dependence, the wave function. So 1 is. Now I have to calculate, let us calculate this. Theta of theta. But for this 0, 0, isn't it? How do you calculate this? Theta of theta 0, 0, just go back and see the expression. It has to be this. Okay? Don't get scared. Are you getting scared? Don't get. Expression I'm giving you. You don't need to remember, but you should be able to do it. So if I do it, what is the answer? So I have to calculate this. Let us calculate the normalization constant first. Okay. So how do I calculate? It is 2 into 0. You say yes. At least I should know that people are there.
Yes,
People
sir.
have not left.
Yes, sir.
What is 0 factorial?
1.
At least you know this. Huh? Good. I'm just joking. Don't take it serious. Let us calculate the normalization constant. What is the answer? 2 plus 1. Tell me.
1. 1.
No. You have to do this.
0.
Math.
1 by
1.
root 2.
Tell
1
me.
by
What is the
root 2.
answer? Yes. Then why did you say 1? Because this is 1 divided by 2, isn't it? And then square root of this, which is 1 by root 2. This is how it is. A convinced? All of you are convinced?
Sir, what about P
Yes,
part,
sir.
LM part?
Now this will, I will calculate this. Thought that I don't remember the formula. I have to go back and check the formula. So I need this formula and this formula. Okay. So let us copy this. So let us copy this. Copy this. I have copied. No, I have not copied. Yeah. Just a minute. I'll do it. Give me a second. Because it should be done live. Otherwise, difficult for people to follow. Okay, I'll need this to for equation, isn't it? Which one should I use first? Tell me. See, I have to calculate PLM cos theta, isn't it? Which is given by this. PLM cos theta is given by this. The second one. Can you see my cursor? But in order to calculate this, I have to calculate PLZ, isn't it? Because PLM cos theta, PLMZ is given by this times
Yes.
PLZ. So let us calculate PLZ. So all these things come from mathematicians. So they knew all this. So we'll calculate this PLZ. Now L is what? Like in this case, P0. Z, I had used small h, but let us use Z here, small z here. Okay, this is equal to 1 over to the power of 0 into 0 factorial. So this is essentially 1, isn't it? And then I have to do d to the power of 0 of whatever, not h, but are you following? It is not very difficult.
Yes, sir. Yes, sir.
Not very difficult. I'm telling you, don't get scared. I'm telling you, I'm with you. Don't get scared. Learn something. Learning is more important than getting grades. So actually, if you take something to the power 0, it basically means it is a differential, no? Basically means I don't do anything, no operation. You understand?
Yes, sir.
Isn't it?
Sir, here Z is equals to cos theta.
Yeah, z equals to cos theta. Yeah, so I write it somewhere here.
Okay, sir.
In earlier notation, 8. Okay. I copied from a book, Pauling Wilson. They had used small z. This small z, okay? 8 in our notation. Anyway, small h. So what is the answer?
1.
Okay, it is 1.
1.
It is 1. It is 1. I hope it is 1. I have not done it. I hope it is 1. But this is only this. And then I have to calculate PLMZ. For this orbital, I have to calculate P0, 0, Z. What is the answer? 1 minus Z square. 0 by 2 is 0. Okay. I hope that I have done these things. If I have done anything wrong, please tell me. I hope I have not done anything wrong. I hope I have not done anything wrong. Okay. Yes. I don't think I have done anything wrong. Yes. Yes. Fine. So this is basically, this is again. But this, the whole, what is the answer? Very easy, because what is the answer? You know, this one. Okay, 1. So basically, theta 0, 0, theta is 1. 1 means because it is essentially this constant, sorry, 1 by root 2, not 1, 1 by root 2, okay? This constant 1 by root 2, and then this is equal to 1. We have found, nah? Okay? I hope you have no problem with this. Okay? Okay, and if I multiply this to what I'm going to get, phi 0 phi into, I have already told you what is this. This is 1 over root over 4 pi. But what is this quantity? Tell me. This is y 0 0 theta comma phi. This is called spherical harmonic. Huh? Fine. It is fine. Is it fine or not? I had did I define this? No.
Yes.
For L equal to 0, M equal to 0. This is how it is, isn't it? Okay. This is a spherical harmonic. So now I am
Yes, sir.
almost done. But I am not done with one more thing. What is it? I have to calculate this. R of 0, 0, R of this orbital, isn't it? How do I calculate this R of 0, 0, R? Tell me. How do I calculate? Again, I go back and take the formula. Okay, is it fine? Are you getting
Yes.
scared? Are you getting
No,
scared?
not really, sir.
Yeah, don't get scared. Only thing is that I'm getting a little scared because the formula I have to put it there, and okay, we'll do it. So we'll do in the next page. That is better. Okay. So let us do it.
Yes, sir.
Yes. Yeah. Because otherwise I cannot manage. You should do it once. So these are the equations, okay? And I have to calculate. Sorry, I have to calculate your calculate R 0, 0.
R10.
Sorry, 1, 0. Yes, right. See, whenever I make a mistake, you tell me. It has to be 1 R 10. You're right. N cannot be 0, no? That's why I need students. Without student, it is very difficult for me to teach. I have to calculate this. What is this capital Z? You remember this capital Z is 1, huh? Because we are doing
Yes,
it
sir.
hydrogen atom problem. So let us do it. This is going to be 2 by A0 whole to the power whole cube. Then this is 1 minus 0 minus 1 factorial divided by 2 into 1 plus 0 factorial. The expression is quite complicated. I think this is how it is. I don't know why we have anything here. I'm not sure. Not sure anyway. I'm not sure. And then you have half here. And then you have e to the power of whatever. E to the power of minus rho by 2 rho to the power of 1 L. Not rho to the power of 1, rho to the power of 0, because you are doing this. L 2 into 0 plus 1 divided by 1 plus 0. Essentially, this one is your L1 rho. And if you calculate the actually you can calculate the coefficient, and if you calculate the coefficients, I think the coefficients are coming out to be this other part if you calculate it properly. I'm not going to do it. So if you calculate this properly, it is coming out to be minus 2. Okay, minus 2
2 over a naught
into
raised to the power
1 by
3 by 2.
a0 e cube. Yes, you can do it yourself. I think this is how it is. Okay. And what I need to calculate L11 rho, which is here. Basically, I have to take a first derivative of L with respect to rho. But what is L rho? L rho is given by this. I have to calculate L1 rho. And L1 rho is actually exponential of rho. First derivative, because R is 1, no? So it is rho. And what is the answer to this? It is rho. This will give me, tell me, it will give me e to the power of minus rho plus rho into minus 1 to the power of minus rho. Is this fine?
Sir, what is R here? R is 1 and
Yeah. So R is this. R is 1, no? So R, whatever this is a dummy variable, the R is 1. This is your R. Whatever this R is. This R is 1. So if I do this, I can take common, which is going to be 1 minus rho. This is what I'm going to get, 1 minus rho. And then I have to take the derivative of this again of 1 minus rho in order to get L11 rho. Isn't it? Because this is the definition. Huh? L11 rho means first derivative of L1 with respect to rho. And what is the answer? If I take a derivative of this, minus 1. Fine?
Minus.
Yeah, so the whole thing is, this will give you minus 1. So the whole wave function is going to be minus 1. And what is the answer? Minus minus I can compare, I can combine. What I have here is 2 okay. Actually I've done it everything like in detail. So I have now R10 R. Then I will do it here. Then what is this? Psi 1 1 0 0 R. R part, theta part and phi part. Huh? R part is this. What is theta and phi part? You remember? 1 by root over 4 pi. I remember that. Spherical harmonic for that. If I go back, I can show you. This is 1 over root over 4 pi, isn't it? If I do this, then can I just rearrange it? Yes, I can rearrange it because I know that this 2 and root over 4 will cancel. This 2 and root over will cancel, isn't it? Okay. So this will give me 1 by pi a0 cube whole to the power of half into e to the power of minus 4 by 2. And this is your psi 1s. If you go and see any book, you will see this is exactly what you have there. Looks familiar to you, this expression?
yes, sir.
But what is rho? What is rho? Tell me.
2z r
Rho
by
is this.
n.
Rho is 2z r by n a0. So in this case, z, capital Z is 1 because I am doing hydrogen atom. N is 1. So what is this rho here? Twice r by a0. Okay. Is it fine? That is your psi of 1s. I'll do it later, but that is how it is. So basically, if I put the rho there, rho is twice. Let's go back here. twice r by a0. So this gives you what? This gives you your expression for psi1 is as psi100, which is your psi of 1s 1 over pi k0 whole to the power 3 by 2 you can write, or you can write the way I have written there. I think I have written like this, no? E to the power of minus, now rho is twice r by a0, which is twice 2 will cancel, minus r by a0. And this is 1s. This is very familiar to you, I hope. I hope it is, isn't it? Because many of you had a course in hydrogen atom. This is your psi 1s orbital. Is it fine? Is it fine?
Yes, sir. Yes, sir.
Yeah. If I plot this, how does it going to look like? A function of r. So at r equal to 0, it is some constant, and then it will decay exponential. Isn't it? So exponential decay. Okay? It is fine, and eventually in the high, when r goes to infinity, it will become 0 asymptotically. This is how it is. Psi 1s, it has no theta or phi dependence. You have seen this. Okay. And how to represent this other than this? There's something called, what I'm going to say the density plot. Today what is known as density plot. So we represent the function by shading. Okay. If the function is negative or positive, we put the sign plus or minus, plus or minus. So in this case, what happens? You see that if I look into the psi 1s, you see that when it's close to the nucleus, your psi 1s has a higher value at the nucleus. So if I make a density plot of the psi 1s orbital, it will look something like this, and as you go away from nucleus, the density will be very badly drawn. But you understand what I'm saying? But it's spherical. Okay, and then everywhere it is plus, because the function is never negative. You have seen this? Function is never negative. This is your psi of 1s plot. Similarly, you can plot psi of 1s square, or mod of psi of 1s square. In this case, real. So that will be similar in this case, because exponential of minus r by a0 will become exponential of minus twice r by a0. Numbers will change, but the plot will be the same. Okay, this is called density plot. And because if I take this is called probability density, isn't it? Like probability density. Now next I ask a question: what is the probability of finding an electron between r and r plus dr, where r is the distance from the nucleus. So I just asked the question: what is the probability of finding an electron within r and r plus dr, between r and r plus dr, where r is the distance from the nucleus? How do you do this?
Psi into psi star.
So in order to understand this, let me do it. In order to understand this, so let us draw something. Let us draw sphere. So let me draw a sphere of radius r. Believe me, this is sphere. You'll not believe, but it is sphere. Okay. And then I have to draw another sphere of radius slightly higher. What is that radius? This one is, this thickness is, dr. This is a radius r plus dr. Is it fine? And then I have a spherical shell here between r and r plus dr. I have a spherical shell between r and r plus dr. What is the volume of the spherical shell? Volume. Can anyone tell me what is the volume of the spherical shell? I have shaded.
4 by 3 pi r.
Yeah, it has to be 4 pi r square. What is the surface area of the sphere? Into dr. Dr is the thickness, isn't it?
Yes, sir.
Okay. Okay. Fine. Now I can always say, okay, now I ask a question. What is the probability of having the electron at a distance, or how possible the distance r from the nucleus? In order to do that, what I need to do, I need to take the square of this function multiplied with this volume element. Okay, and I call this quantity without the dr, this I called what is known as radial distribution function. Okay, this is called radial distribution function because it tells you what is the possibility, how possible the distance r from the nucleus. Essentially tells you. Now, what do I mean? See, look at carefully this expression. I have multiplied this with dr. If my dr is increases, the whole thing, the value of the whole thing will increase. Okay, so the whole thing, it is this whole thing is like a probability density, and you multiply it with dr. This is probability density. Sorry, psi 1 x square is probability density, and you multiply it with this quantity that gives you the total probability. Okay, and this is quite useful when you plot this. You can plot this function, and let us try to plot this, because this function when you plot as a function of r, you will see that you'll be able to answer question like what is the most probable distance. Okay, so let us try to do it. One thing I must say that I have not told you, that if I have a volume element like dx, dy, and dy in coordinates, when I go to spherical polar coordinate, that becomes r square sine theta d theta d phi. Okay, you remember this. Okay, I'll show you the derivation. Okay, now if I plot this probability, the radial distribution function.
The dr term will be there.
Yes, you're right. Yes. Radial distribution function. Now, if you plot the radial distribution function for the 1s orbital, I have seen what is this. This is psi of 1s whole square times this. So psi of 1s whole square is going to be, what is that? Psi of 1 plus. It was like no, that we have written. So if you take a square of this, then multiply this with 4 pi r square into, okay,
So,
what is the
so,
answer?
so it was 1 by pi aq to the power 1 by 2, not the whole term will not be to the power 3 by 2.
Okay, okay, 1 by pi a to the power, okay, it is not the okay, 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 okay. So I don't have pi to the power minus 3 by 2, I have pi to the power minus 1. Okay, I understand. Pi to the minus half. Okay, I'll write it the way it is written. It was like this. Let me check. 1 by a0 cube to the power half, isn't it? It is like this. Okay. So if I do this, what I'm going to get? I'm going to get some constant. I don't care about the constant. But you'll see that you'll get something like, it has a structure like r square times, okay, with constant and multiplied with the constant. This structure, okay. So if I plot this, how I'm to, so if I plot this quantity, radial function for 1s, look at it. When r is 0, when you are close to the nucleus, the good thing about it, if you define this way, you see the probability density, probability of finding at the nucleus becomes 0. This gives you physical. So it starts from 0 and then it should increase because of r square. So r square is like a parabola. It should increase like this. But then you have exponential decaying term, exponential minus 2r by a0. Eventually it will increase and then it will go to maxima and then decrease. And asymptotically, it will become 0 when r goes to infinity. Is it fine? So basically, it has a maxima, and I'll see what is that maxima. R max. This is called the most probable value. Most probable R. How do you calculate this most probable R? How do you calculate?
Sir, D probability, DP.
Yeah. You have to take this radial distribution function, whatever. Take DDR of this thing. You have some constant. I am not writing. R square exponential minus goes to 0. And if I calculate this, I'll get R most probable, that is equal to a0. You can go and check. And this is nothing but Bohr radius, the fast Bohr radius, isn't it? Okay, this is a radius for the fast Bohr orbit, rather. Okay, I am not going to do the differentiation. This is very simple. You can do it. Product of two functions. I've done this thing so many times. So this is how the radial distribution function looks like. And let me do it for another function, which is psi of 200. Can anyone tell me what is this function? It is 200.
2s orbital.
This is
2s orbital. 2s.
Yeah, this is 2s orbital. Okay, this is like psi 2s because n is 2, so that's why 2, and 0 is L is 0 and m is 0. It has to be 2s orbital. And if you see that, if you do, I'm just going to write it down, the expression. So the expression for this is 32 pi A0 u all to the power of half 2 minus r by 0 exponential of minus. Okay, so I can plot the radial part of the wave function, basically plotting psi of 2s. If I plot this, what I'm going to get this function, some constant times, it's a structure like a constant times 2 minus r by a0 into exponential of minus r by a0. Okay, fine. If I plot this, what I'm going to get? Can you tell me?
There will be one node.
Yeah, node, but how? So let us do it. Only one person is telling.
So it will start from a point and then at r equals to 2a naught, there
Yeah.
will be 0.
See,
Then
first of all, whenever I am first of all, it is, if you try to plot this as a function of r, you have to try to function of r. Whenever you're in the region that, okay, your r by a naught is less than 2, then this quantity is positive. Okay.
Yes,
But
sir.
when r by a naught equals to 2, this quantity becomes 0. Okay. And when r by a naught greater than 2, this quantity becomes negative. If you have something which is positive, 0 and negative, and the other part, exponential of minus r, is always positive. Okay, it can be 0 in asymptotically, otherwise it is always positive. And it's decaying function. If you plot this, you will see that it starts decaying like this, but it is positive and decaying. But then, because of 2 minus r, as r increases, 2 minus r value decreases. So it will make the function to actually decay, and then when you are approaching 2a0, when r is equal to 2a0, the function becomes 0. But again, now when your r is greater than 2a0, your function becomes negative. It will become negative. But again, you have this exponential of minus r, which will ensure that in the r goes to infinity limit, you get 0. It will asymptotically become 0. So this point is r equal to 0. And this is a point where the wave function becomes 0. So if the wave function becomes 0 at a point, or for some value of the parameters r in this case becomes 0, this is called a node. More precisely, this is called a node when the wave function changes sign. It becomes, it is plus here, and then it becomes minus, it has to go through 0. So it is called a node. So this is a node. So you have a node here. And this is a special kind of node, and this is called a radial node. You'll see. Because it is along the radial direction, isn't it? It is in R. It's called radial node. And if I make a density plot of psi 2s, can anyone tell me what is going to be? So whenever I am between 0 and 2a0, so it is this quantity is positive, but it will decay. So it is something like this. And then exactly at r equal to 2a0, what you have? You have a node, radial node. I hope you are following. You have a radial node at r equals to a0. So I will have a radial node at r equal to a0. I'm just showing it with a red thing. And then whenever I go beyond r equal to a0, what is going to happen? Tell me. So I'm going to have similar thing, but in this case the things will become negative. Basically here it is negative, inside it is positive, and you have a radial node here. Okay, and you can do the same thing for psi 200 square, but in that case everything will be positive. If I take a square of this, everything is going to be positive. Now I can do the same thing what I have done with psi 1s. I can actually plot this, the radial distribution function for. Can anyone tell me what is going to be? I can actually, you can see that it is not very difficult. You can go and see how it comes out. If you plot is a function of r, what you're going to get? So you have this 2 minus r0 whatever. You have a square. So you'll have 2 minus r0 whole square and then square of this times r square. Remember, times r square. So can anyone tell me what is going to be?
So there will be two Gaussian kind of.
So that you remember. Basically, you have something like 2 minus r whole square, okay, into exponential of minus what is that? R by a 2a0. So basically, you know, r by a0 into 4 pi r square. And this 4 pi you can put in the constant. So anyway, so essentially you have r square 2 minus r a0 whole square exponential of minus r by a0. The good thing about the way it is defined is always positive, isn't it? It is going to be always positive. Are you convinced that it is going to be always positive? Okay. And you'll see that as somebody pointed out, if you plot this, I think it will be at r equal to 0, because of this r squared term, it is 0. And for this exponential term in the long, for large r, it is again 0. So actually it will start like this, go like this, it will come back at some value, hit 0, again it will go and go like this, and then you come back and eventually it will become 0. So there are two most probable. This is one, this is one. Okay. Can you tell me when it will be hit 0? What is the value of r? Just by looking at this expression. When is this function going to be 0? Tell me.
So 1 at 2a naught.
When? Look at that expression and tell me.
So r equals
Look
to
at that
2a naught.
0.
Yes, because when r equals to 2a naught, this quantity is 0. So essentially r equal to 2a naught, it will be 0. And also you can take a DDR of this. Okay, this is not psi 2s. Okay, this is okay. DDR of this whole thing. Put it 0. You will find there are two possible values. Most probable, I call it 1, and most probable 2. The 2 is the second one. I will see that the peak for the second one is higher, and that is actually most probable. You can try to find out what are the values, what are the a0 values in terms of a0, what are the values of r. That
Sir?
you can go and find it out. Yes, tell me.
Actually, if we do the derivative, then we will get
Yes.
3 values of r.
Try doing that.
Yes, I
Try
have
doing
done.
that. Yeah. So what about taking second derivative? You have to know whether maxima or minima, no?
Yes, actually,
First derivative gives.
at r equals to 2a naught, there will come another, means it will be also
Yes.
0.
Yes, of course.
Because the tangent is 0. Means, yeah.
Yes, so basically you have to take the second derivative also, no? To know whether it is maxima or minima, isn't it?
Yes, sir.
Yeah, that you do. Yeah, I'm not going in detail. You can just do yourself and um, get it done. Now let me do one more thing. As doing this, let us write down this 210. Can anyone tell me what is this orbital?
2B.
This is n to l equal to 1. L equal to 1 gives you what is known as p orbital. So basically this is, and z equal to 0, not z, sorry, ml equal to 0. This is called actually 2pz orbital. Okay, we'll talk about it more in the next class. I don't need remember. I don't want you to remember this. If you write down the expression, and here you will see that it has a no phi dependence, but it has a theta dependence, and this is cos theta. Remember, z equals to r cos theta. Remember, no? From there, this cos theta dependent comes. Okay. So this is psi to pz. Now how to now it depends on so essentially it depends on the angle theta. What about the radial part? How does it look like, the radial part? So r21. If I plot it, how does it going to look like? Tell me. Your r times exponential of minus r minus, isn't it? So it will, the radial part would look like this. So like this. It's fine. Because your r equal to 0, it gives you 0. The radial part of this. Radial part means this part. With some constant. This is r1r. Okay. If I plot it. But how to plot the angular part? Any idea how to plot it? How to plot the angular? How to represent the angular plot? How to plot or represent? Any idea? Any answer? Maybe in the chat box you tell me how to represent that.
So actually theta, if we know the value of theta, then we will have that thing. Means theta
I
is
don't
the
know whether you, I don't know whether you know what I'm going to do. I'm going to do what is known as polar plot. How many of you know polar plot? Write in the chat box. I'm going to make use of what is known as polar plots. Okay? How many of you know polar plots? Tell me. How many of you know polar plots? Heard about polar plots? You guys said that you know hydrogen atom, so that's why I'm asking the question. Write in the chat box. How many of you know polar plots? No one? Heard about polar plot? No idea. Then you don't know hydrogen atom. Not because of the polar plot. Then you should know all these things. Okay. So the polar plot I'm going to do, but before I do this, I make a table of theta and cos theta. Theta is 0. What is the answer value of cos theta? 1. If theta is, these are all in 30-degree radian, then what is the value? 0.85. 60 degree, any idea what is the value? Not the 60 degree, 45 degree. What is the value? 45 degree. Okay, let me write it down. Okay, 0.7071. 60 degree, you should be able to tell me 0.5. What is cos 90? 0. I hope I'm not doing anything wrong. If I do anything wrong, 120 is minus 0.5. Okay. Then 135 degrees minus 0.7071. Okay. Then 150 degrees minus 0.85. Okay. And 180 degree is minus 1. Okay. And the idea is as follows in this case. From the origin, I go along any axis. Say I can go along x-axis. If I go along x-axis, what is the value of theta along x-axis? How many of you remember? Go back and tell me what is the value of theta along x-axis. Write in the chat box. What is the value of theta along x-axis? Because I have to finish in 5 minutes.
Sir, 0, 30, 45.
No. Value of theta is the angle between z axis. No. So if we're along x-axis, theta is 90 degrees, isn't it?
Yes, sir. 0, 90, 180, 270.
No, don't go like this. Go to your spherical polar coordinate. Remember, we had this. This is x, this is y, this is z, and this angle was theta. Remember? So if you
Yes,
are
sir.
along x-axis, your theta is 90 degrees, isn't it? This is how it is. Has to be, no? Because this also makes, if I or even y-axis, it is 90 degrees along x. Or even you can go along y. If it is, you don't like it, you can let us go along y. Theta is 90. This picture, this is 90 degrees. So the point is that, okay, you choose one axis. Say, let us choose y-axis, and from the origin I go along that axis. Theta is 90 degrees. If I go along z-axis, what is the value of theta along z? What is the value of theta along z-axis?
0 degrees.
I asked 0. Now I make a plot that I go along some axis. I know the values of cos theta and cos theta. So now I calculate for different values of theta the value of cos theta. But whenever the cos theta becomes negative, I take the absolute value of that quantity and plot it. Okay. And this is called polar plot. So how to do it? We'll do it again in the next class. Don't worry. So I have two axes, for example, z and y. So when I'm along z axis, your theta is 0. Along z, theta is 0, isn't it? Along z. So what is the value of cos 0? When you're along z, it is 1.
1.
So I put a point here, 1. So this is 1, this quantity. From the origin, the distance is 1. Okay? Next, I make the value of theta 30 degree. What is the value? The value is 0.85. Can you see? When theta is 30 degree, what is the value of cos theta? 0.85. So 0.85 is less than 1. So I'll put a point here. When theta is 30 means this one, no? This is 30 degrees. Okay, so that's why I put the value, and this value is, so this quantity is 0.85. This length is 0.85. Okay, and I keep on doing this. I can keep on doing this. Once I keep on doing this, this is 1 at 0 degree, this is 0.85 at 30 degree, 0.70 at maybe 45, this is 0.5 at 60, 0.70 is here. Then at 90 degree, what is the value? It is 0. And if I go beyond 90, what is the value? 120, it is minus 0.5, but I take only the absolute value. If I take only the absolute value, what is the absolute value of minus 0.5? It is 0.5. Okay, so again when I go to 120, I'll take this value. Again 135, minus 0.70 I cannot take, I take plus 0.70, which is something like this. 150 minus 0.85 will become plus 0.85, and again 180 it will become 1, and I then join this point. Sorry, so I think because this is how I join the points. This is 85, okay, and this point, and then I know that in this half this is plus, on the other half this is minus. I just remember and put that sign, and I can complete this, although theta varies from 0 to 180, but I can also complete on the other side because it is equivalent, and if I complete this I'll get a plus and a minus here, and this is the polar plot of cos theta. We'll stop here. Only thing, plot only the absolute value. Is this fine? But once you are done with plotting, remember that when it is plus, when it is minus, so you put minus here and put plus here. So stop here. So whenever you have an angular dependence, you have a polar plot. And one thing you have already noticed. So if I take n equal to 1, you have psi 1 0 0. Okay. For n equal to 2, what I have psi 2 0 0, psi 2 1 0. What else? Anything? I should also have psi 2 1 plus 1 and psi 2 1 minus 1, isn't it? And they will have same energy. Are you convinced they have same energy? Why? Same n, because energy depends on only the principal quantum number. So for n equal to 2, there are 4 wave functions or 4 orbitals, and they have the same energy. So I'll call this is 4-fold degenerate, this level, isn't it? So energy depends only on n, principal quantum number. Okay, so we'll start from here. Thank you very much, and please go and watch what is known as my recorded video, and I will stop here, and the next class is on Friday. Okay, thank you. So I'm stop sharing, and also I'm stop recording.